title of my talk is Artificial Neural Network for Hoax Cryptogram Identification. I'll give you a little bit about my background first of all, because I think so few of you will know who I am, but my background's actually in physics, and I'm currently studying for a degree in data science and statistics at Leeds. I have published a little bit on cryptography before, but I'm still pretty new to historical cryptography. My most notable contribution in cryptology was on the Rogue cryptogram, but I'll be talking about a different cryptogram today. So as some background, many putative cryptograms remain unsolved. We all know this, and if you don't believe me, see the lists by Schmey and Dunin. Some have remained unsolved for a really long time. The last Beale cipher, I think, that's been going on a very long time. The Voynich manuscript drew modern attention in 1912. And then, of course, the Dorabella cryptogram, which my talk will be on a little bit, 1937, that was published. We have a problem here, though, which is that it's really hard to tell which are really cryptograms and which are not cryptograms. There's a couple of different things it could be. It could be a hoax, it could be an art project that was never meant to be a cryptogram at all, but people are misinterpreting it, and so on. So it'd be helpful for us to know where we should focus our efforts, which are more likely to be cryptograms and which are not. And it's also really important to remember that an absence of evidence is not evidence of absence. Just because we haven't found a solution yet to some of these ciphers doesn't mean that we never will. And a great example of this, I think most people here will know, Z340 went unsolved for 51 years, and then very recently Blake and et al. Figured it out. But it was even studied potentially as a fake, and some people thought that maybe it was a hoax. So I think we kind of need to get our heads around which ones are more likely to be real and which ones are more likely to be something else, non-cryptogram. And this can be seen as a categorization problem, right? So in machine learning, we have this idea of categorizing objects into different groups. The idea here would be categorizing putative cryptograms in those that are more likely to be real and those that are more likely to be not real. Now, someone took issue with me yesterday for using the word hoax. So I won't use the word hoax. I'll just try and say not real or gibberish. But machine learning algorithms have been developed to tackle exactly this kind of problem of categorization. You have, for example, studies that categorize a species of bird just by its vocalization. If you don't know what the species was, you can put it into the algorithm that's been trained, and it'll give you a probabilistic output, tell you what it's more likely to be. So in this work, I look at a simple neural network to categorize real texts and gibberish texts, and I have an application to the Dorabella cryptogram, but I don't want you to all get your hopes up because I've not got a solution to the Dorabella cryptogram. It's still unsolved, and I think you should also take the work that I'm presenting here with a grain of salt very skeptically, because I'm not really quite convinced of my own findings, to be honest with you. So if you don't know the Dorabella cryptogram, that's a picture of it up there. I think that picture's in the public domain, and if not, please don't sue me. I don't have that much money. The Dorabella cryptogram is apparently a simple substitution cipher. It's prepared by Edward Elgar in a letter to his acquaintance Dora Penny. We assume that it's a simple substitution cipher, a mask, because we have other writings by Edward Elgar that very clearly are simple substitution ciphers, and yet you try and apply some of those solutions, or even just throw it into AZ-Decrypt or Cryptool2, and you don't get a convincing solution. Part of the problem is that it's too short, which I'll brush on maybe later, but no solution has been generally accepted by the cryptologic community. So this begs the question, what is it? Is it a hoax? Well, some people have alleged that Elgar was cruel, or is it something else? Maybe it's a different kind of cipher. Maybe it's not a simple substitution cipher at all, but something else. The question of why I looked at Dorabella in this, well, for one, it's very well known and well studied, and for two, it's very short. It's only 87 characters, and the unigram alphabet's actually only 20 characters, 20 unique characters. So it lends itself to a simple analysis of the kind that I'm presenting, just as like a proof of concept. So I developed a machine learning model in Python with TensorFlow and Keras. There was some interest earlier in the kind of hardware people were using. I'm literally just running this on a 64-bit Linux system, just a laptop, no distributed computing, no GPUs, nothing like that. Very simple model, just a 2-layer sequential artificial neural network. And I use this to categorize text as either real or gibberish. I trained this network on 2 evenly balanced data sets. I generated 10,087 character texts from English Wikipedia articles, and there's an example there of what it looks like. So Tern was invested with the duchy for himself and his heirs. Albert's rule in Prussia was fairly prosperous. So you can look up, that's actually from the Wikipedia article for this guy in Prussia. And then for the I shouldn't use the word fake, I've been told off for that. For the not real or gibberish data set consisting of 10,087 character gibberish texts, Those were randomly generated from a uniform distribution, so taking every letter of the alphabet, given an equal probability, so 1/26 of being selected, and then just sequentially or randomly selecting one letter at a time. And that's the kind of gibberish you can see, like I, D, Q, B, N, J, B, N, A, L, just gibberish nonsense. I fed these into the algorithm, and the hope is that the real text will act similar to a substitution cipher, because you're not really changing any of the properties of the text, you're just changing kind of the appearance of the character, and that any fake text the idea is that if you fed a hoax into it, it might act more like the gibberish text. Maybe, I've got the caveat there, maybe, and I'll come to that at the end, because I think there's kind of a novel contribution of this that is not touched upon here. So the properties of the text that I fed into the model, so I didn't just give it the texts and let it go wild. I told it, okay, this is what the alphabet length of the text was, so literally the number of unique n-grams, that for unigram, bigram, and trigram. What is the average frequency of those n-grams? What's the distance? And by that I mean the mean number of steps, if you like, between the same character occurring again. The entropy, index of coincidence, which measures the evenness of the distribution of characters. Zipf's exponent, this comes from Zipf's law, which it kind of describes natural languages, and the average mean associated contact counts. All of the details on these, if you want to look up the equations that I use to calculate them and so on, they're all in the conference proceedings there. So if you can look that up if you're interested. They are quite technical at times. And the idea is that these properties all represent statistical and linguistic characteristics of each text. So hopefully, if it works, then there should be a real difference in these properties for those texts that are real, kind of English language corpus texts, and the texts that are gibberish, and hopefully we can distinguish between the two that way. So this is the table of results. The first column there is the statistic, and then the next column for corpus, that's the English language texts, the properties for those. The last column is your gibberish, randomly generated gibberish texts. I'm showing the mean and standard deviation properties across text because there were 10,000 of them, so I'm averaging across for the real and the gibberish data sets. And you can see some properties were actually quite similar, so the average trigram frequency and entropy didn't differ that much, but others did differ descriptively. So if you look at the properties that are in the green highlighted boxes, those differed quite a bit. So the alphabet lengths are quite different, average bigram distance quite different, average unigram entropy quite different, and some of the others too, like the average mean associated contacts count at the bottom there, but you look at the standard deviations quite right, there's a lot of variability across the distribution, so some of these distributions do overlap. Next, let's look at the model that I built based on these texts. So the model actually had an average accuracy of 99.8%, which sounds very good, but I'll warn you, it's like with COVID tests. If you give it to 1 million people, 99.8% sounds great, but you're going to get quite a lot of false positives. So don't be too allured by that fanciful high accuracy. But I did use 5-fold cross-validation to try and reduce some of the bias of the testing and training data sets. Now, the Dorabella cryptogram, if we look at the same properties, these same statistical and linguistic properties, it tended to group more closely with the corpus, that is the real texts, than with the randomly generated text. The purple boxes are the ones where it was closer to corpus, blue boxes are the ones where it's closer to gibberish. So I think there's 5 gibberish it was closer to, and then I think 8 corpus that it was closer to. So I did some out-of-sample tests on this model. I threw in an 87-character simple substitution cipher that I generated with the Practical Cryptography website, and it correctly identified that as real with a probability of 0.99999. Now, I also don't want you to take this as a measure of precision. The reason I'm adding so many decimal places here is because if I were to round it, it would just round to 1.0, and then I don't really think I'm saying it's 100% probability, or 100% chance probability of 1. I also fed into it a randomly generated text from random.org, and it correctly identified that as randomly generated gibberish with a really high probability as well. And then for Dorabella cryptogram, the interesting thing is I fed that into the model, and it does think with a pretty high probability that it's more likely to be a corpus-style text than a uniformly randomly generated text. So, in summary, it does appear that a simple neural network can accurately distinguish between those that are kind of English corpus language texts and those that are pseudo-randomly generated gibberish. This is not the first time people have applied machine learning to historical cryptography, and in fact I'm building upon the works of others here. There was a model that looked at Z340, and then the main one is the neural cipher identifier, which is a much better model than the one I've built, but that model does not include a fake text category, so it only will go through all the types of possible cryptograms, and it will give you a probability for a text that you enter into their model, but it won't say, okay, actually here's the probability of it being fake. There are lots of limitations to this work, lots and lots. So, for example, I only looked at English language. For all we know, the underlying plaintext could be German or French or so on. It's not 100% accurate, and like I said earlier, high accuracy models can actually be quite misleading. And the training sets may not be representative. So I obviously trained this model on Wikipedia English language corpus versus uniformly randomly generated gibberish. But humans don't produce uniformly randomly generated gibberish. In fact, if you ask someone to simulate the roll of a die and give you numbers from 1 to 6 randomly, it's very unlikely they'll give you 3 6s in a row. But if you were to roll a die, it's really likely that you can get a combination like that. So that I think is sort of the novel contribution of this work, is actually just asking another research question that I came across, which is how do we simulate human gibberish as opposed to uniform computer pseudo-randomly generated gibberish? And if you could do that, if you could, for example, maybe use a language model that imitates human text better and get it to give you what its idea of human gibberish is, then maybe the model that I've built could be much improved. I did ask someone here who's an expert on this question, and their solution was you need 10,000 monkeys on typewriters. I don't know about the ethics of that. I don't think I'd get IRB approval for that sort of research, and I also don't have the resources. But if you know anyone who has 10,000 monkeys with typewriters, then please let me know and we can get working on this. So I think that future work, definitely adding multiple possible fake text categories. So we need a more human-like gibberish, I think, than a machine computer-generated gibberish as a comparator or a category in the outcome. And we should look at more languages. And really, I think my main recommendation is if there's anyone here who worked on the NCID, the neural cipher identifier, it would be great if they could add a fake text category of the kind that I've shown here, or better, to the NCID, because currently I think that would be the best approach. And then just finally, what is the Dorabella cryptogram? Well, the model seems to suggest that at least if you compare it to Wikipedia-style English language corpus and uniformly generated random gibberish, it seems more likely to be the former than the latter. And this might be consistent with some indications from recent research. Schmey and Hauer et al. Found evidence that maybe there is some kind of underlying English plain text of a Dorabella cryptogram. But there are lots of other possibilities too, right? What about a non-simple substitution cipher? What if it's not random gibberish? What if it's not English? So no convincing solution has yet been found, even using really modern state-of-the-art algorithms with high decipherment rates. So that this is maybe more evidence that might lead you to believe that perhaps it's real, but we do have to take the example of Z340, where some people had studied it and thought maybe it was fake and then turned out to be the opposite. So I would take these findings very skeptically, and I think that more research is needed. Those are my references, and I know there's a Q&A. So if you don't mind speaking into the microphone and speaking loudly, I do have hearing problems, so hopefully I'll be able to hear you. And thank you very much.